Okay, hello, hello, and welcome back to one of my video recording sessions, video log recording sessions, where I talk about genetic algorithms. And the date today is 2025 May 18th, and before I get actually started, let me just give you an overview of what I'll be trying to do today in this session, as this session may result in not one but 2 or even 3 parts, depending on how long I end up dragging it out, or how much I get distracted, or how much I don't get distracted, because there's so much for me to cover, so many different combinations and possibilities for me to cover. 1848 to be exact, so it's not little. So today I am going to be covering 13 Jupyter notebooks. I know that is the most numerous I have done so far, and I hope I'll never have to do a session like this ever again, meaning a session where I have to cover more than 3 notebooks at a time. But for now it is what it is, and I'll just try to soldier on and plow through it where I can. So, why 13? On the screen right now, you'll see these lines in red. People love red lines, don't they? I know that was a terrible joke, but and however, or whatever. Anyway, so however, if you count the number of lines in red, you'll find that there are 14, and that is because this one I will choose not to do, and as this one is for anyone who have watched my video logs, previous ones, I mean, you'll remember that I talked about the 2 options that I have when the entities are given the chance to learn from other entities, usually in this case the top 10%. So and those two options were the newborns would be added first, and then the learned candidates would be given the chances to learn from the top 10% entities. And usually when the newborns are added first to the front of the list, front of the world, that is it, which is a list, the newborns are usually included in the top 10%. So in other words, the learned candidates will be mostly learning from, are very more likely to learn from newborns, which is okay, as newborns are in most cases the next generation, by definition, and they're much more likely to have slightly higher sum utility scores, individual sum utility scores. And the second option was the second option is where the learned candidates get to learn first from the pre-existing top 10% of the world, and then the newborns would be added to the front of the list. Yeah. So that's that. And then once all the learning is done, whether it's add first, learn later, or learn first, add later, the shuffling will come into play, and the list is shuffled, so that the population limit function doesn't just discriminate against the entities with low individual sum utility scores. So those two that I talked about were these two. And then in one of my past videos I said that I will focus more on add first and learn later, as this does yield somewhat better results. Of course, the word better has many aspects to it. Better isn't always better. Better isn't always more good. It may sometimes actually be bad. But in this case, I mentioned that it was a sacrifice I was willing to take. Not sacrifice. Let's just say compromise. Yeah. So this one is going to be crossed out for now. So forget that. So that's one. And then 6 cases up above. The notebooks, or rather the evolution result folder titled 2025-0513 underscore 0 to underscore 5, so 6 folders, 6 directories. The ones with 13 underscore something are where the learn rates are fixed. So and now I've come to call that as universal learn rate, meaning the learn rate for every individual entity is the same. From if it's set to 0.1, then it is the same for the top entity, the head entity, all the way to the bottom, all the way to the tail entity. And if it's set to 0.0, then it's 0.0 for everyone. If it's set to 0.7, it is set to 0.7 for everyone. You don't get different learn rates for different entities in this case. So that's another 6 notebooks just added. And then the next one, where they're titled 2025-05-14 underscore 0 or underscore 1 or 2 or 3 or 4 or 5, all the way from 0 through 5, exactly that. And by that I mean where the learn rates for individual entities may be different or can be different, because they're assigned different individual learn rates by a function, by a distribution, by a function that uses a certain type of distribution that is stated or clarified. So for example, I'll finish talking about the learn rate and then the candidacy. So learn rate can be, as I think I've mentioned this in my last video. Let's get rid of that for now. For example, if I had the world here, this is the world, and then for every entity, usually 1000 or about 1000 of them, individual learn rate will be assigned or computed and assigned. And this learn rate, this is world before shuffle. So the learn rates can be assigned by different distributions. So if, for number 1, if it's a uniform distribution, then no matter what rank you are in the world at that point in time, within that generation, every entity is likely to have a learn rate ranging from 0.0 to 1.0. But however, it's called uniform because 0.1, 0.0 to 1.0. So they're all likely to be picked for each learn rate. It doesn't matter if you're at the head, if you're the head or tail. The tail entity could get a learn rate of 0.9, and even the head entity can get the learn rate of 0.9. But so everything is random from 0.0 to 1.0. They're all random. Every one of the 11 learn rates, because I cut them off at the 0.1 mark. So it goes from 0.0, 0.1, 0.2, 0.3 all the way to 1.0. So that's 11 learn rates, and all of them are well, they have the same chance of being picked for each entity. So that's why it's called a uniform distribution. So next up is let me just get rid of this. Next up that I can describe, explain, is the I'll just write a big W here, the proportional tail, and this is the head entity, this is the tail entity, meaning this is the top, this is the bottom, and proportional tail could actually have a learn rate. Well, the learn rate method stated as or given the argument of proportional tail will give learn rate that favors entities with low sum utility scores, but in a proportional manner. So something like this, like a linear relationship. And whereas I talked about this in my very last video, and the proportional head in this case would be the exact opposite. Oops. Something like this. This is proportional head because it favors the head, and the maximum learn rate would be 1, and the minimum learn rate would be somewhere close to 0. And the exponential tail would be something like this, but would be something exponential but still favoring the tail. Exponential head would be the exact opposite, just the mirrored version, where the maximum is 1 and the minimum is 0 point something, or just that 0. And so that's so I just explained 5 of them, and the last one would be a normal distribution. So in this case, the one in the very middle would have the maximum learn rate, that is 1.0, and the one at both ends would have the minimum learn rate, which is very close to 0. So these I've just explained 6 learn rate methods, and plus, if the learn rates are fixed, then it's called, I might call it learn rate universal, as in the method is universal because they're fixed. Yeah, so 6 plus universal, that's all you have to remember. And then the candidate method is quite similar, as you have the world, and then for proportional tail, this is the head, this is the tail, and proportional tail, it means that the tail entity has the highest chance of being picked, and then it just goes down gradually. Proportional head is the opposite. Exponential tail would be, you guessed it, it would start at the highest, at the maximum, but it's not 1. It's just that the tail entity would have the highest probability of being picked as one of the candidates for learning, given a candidate percentage. So, for example, if you had the candidate method at proportional tail like this, and then the candidate percentage, CAND perc, was set to 20%. According to these distribution, or according to these likelihoods, 20% of the entities from the world will be chosen. If it's 100%, then it doesn't actually matter, because we're all going to choose. We're going to choose all of them, as it doesn't allow replacement or repeats. So if it's 100%, we choose everything. If so that's proportional tail, straight, sort of like a straight line. That's proportional head. That's exponential tail, exponential head, random, as in uniform. Every entity has the same chance of being picked. And uniform. Yeah, so the one in the middle would be the most would most likely be picked as one of the learned candidates. So that's what that's the 6 candidate methods, candidate methods or candidacy methods. And then if we come back to 2025 this one, 2025 0506-1, where it was universal learn rates and candidate ranges. So in this case, the candidate method, in that case, the candidate method will be range, yeah, and then the ranges will be 0.0 to 0.0, 0.0 to 0.1, 0.0 to 0.2, on and on and on, to 0.1 and 0.0 to 1.0, and then starting from 0.1 again to 0.1, 0.1 to 0.2, and on and on. And if this goes on, you get, I guess, 66 ranges. And that's exactly what I, for so many times, maybe not that many times, but for a few times mentioned here. So that's this. So, recap: 6 learn rate methods plus universal, and 6 candidacy methods plus range. And picking this along with this gives us this 726 different combinations or combos that I have done a video about previously. But today I'm going to go through the rest of the possible combinations. So that was rather a long introduction. How long was that? That was 20 minutes of introduction. But, well, I had to do what I had to do. So anyway, the first one is just like a should I do a recap? Yeah, why not? Or I can just start from this one, oops, start from 2025 0513 underscore 0, that is this one, and then start comparing this to the very first one, which is the one that I already did a video about, 2025 0506 underscore 1, where there are 66 candidate ranges, and with the universal learn rate ranging from 0.0 to 1.0. So let's start. So first I'm going to have a look at the entity counts. I don't think I've done this before, or maybe I have, maybe I forgot. So this is the entity count, and this is what you get. You'll see the red line is the 1000 mark, meaning well, because the population and the max population are all set to 1000. And what you see here is that as the candidate percentage, in this case, if you look closely, I'm just going to do that. Oops, sorry. Seriously? Yeah. So if you look closely, you'll see that the population does decrease a bit as the candidate percentage goes up, which is well, obvious if you think about it. I always say that word obvious so many times, but I don't think I'll stop saying it today. As the candidate percentage goes from when the learn rate is 0.2, for example, it will start going down when the candidate percentage is at 60%, and at 0.3 learn rate 0.3 meaning 30%, it will start going down at 0.4, and the higher the learn rate goes, the earlier it starts to dip under 1000, which is again obvious. Yeah, I mean, this is an anomaly as well. If you see here, I don't know if that's actually an anomaly, but when the learn rate is at 100% and we are picking 100% of the world as candidates, it actually gives us more entities than when it's at 0.9. This could be because of the fact that since everyone is learning from the top 10%, well, it gets less and less likely that the entities get struck out. Could be. It's just a speculation. I'm just guessing. So, did I mention what this is about? This is 2025 0513-0, which is where the candidate method is proportional tail, or proper tail, and then we have the learn rates set to universal, or rather we have 11 fixed universal learn rates. So this is and so when we compare the world entity counts, as in how many entities there were in the final world when the evolution iteration ended, this is 0506-1, 0506-1, and then when we have a look at that, this is what we get. So quite similar. The fact that there are fewer entities as the effective learning goes up doesn't change. Yeah. So moving on to limited entity counts. So well, here the number of entities that get limited, that actually end up being limited by the population limit function, goes down as the learn rate goes up, or rather the effective learning or the impact of learning gets bigger, because well, it could be due to the fact that when the evolutions are being carried out, the selector function does its work first, and then where is it? I'm just checking. Yeah, so the selector function does its job first, and then the population limit function gets to do its job. So and once the selector function has done its job and the population is already lower than 1000, well, then the selector function won't have any entities to mark as being limited out of the population, and therefore the number of entities being marked as, number of entities being limited out naturally goes away, as more and more entities that might have been limited out of the population get struck out first, which is apparent when you look at this. You see a similar pattern here, where the limited entity counts decrease, the struck out entity counts increase. And if we just overlay everything on top of each other, this is what we get. And after when the learn rate is at and above 0.3 or 30%, we end up creating more entities through procreation, usually, because we are striking more and more out than we limit them out. I just need a mint. And if you look at the previous ones, that is exactly what happens here as well. More of them, and if we overlay them, you'll see that when the learn rate is at 0.3 and above, the same thing happens. And this is the total entity counts. They start increasing. Same here. Yep. And I thought this would be fun to look at. Next up is entity count ratios. And I'm just dividing the number, in this case, in the first case, I'm just dividing the limited entity count by the world entity count. They start way up there and then start falling down as well, as there are fewer and fewer limited entities, because the ones that would have been limited out of the population get struck out first, which is apparent here. So where this decreases, this increases, which is the same here. You'll see these white spaces, white gaps, filled by these blue spikes. Yeah, and struck out entity count divided by limited entity count. So here I am already supposing that there are usually more struck out entities than limited entities, which is true because none of them actually went. Well, sometimes they do. They do go below 1, but the point still stands at around learn rate of 0.2 or 20%. And we are going to have a look at the entity distribution. I think I should do that later, not in this immediate session, because this is a huge job. But let's just have a look at the lifespans first. Skip all this. Yeah, world average ages. All the average ages. There we go. We see everything spiking up to 300, or maybe above 200. When we had the universal learn rates and the candidate ranges. However, when we have the universal learn rates and when we're using a proportional tail as the candidate method, the average age of entities in the world don't go up as high as 200 or even 100. These two plots are the same scale. As you can see, it starts from 0 and ends at 300. Starts from 0 and ends at 300, and that is the same for the other notebook files as well. These plots, so that the difference is easily noticeable or more noticeable. So that's the difference there. And for the limited average ages, we have this. This is from the 0506_1. We have this kind of like a very between 40 and 30. That's about 36. So we have this plateau. I don't know if I could actually call that a plateau. Anyway, we start at this flat plains, and then we start hitting these chasms, which is somewhat similar here as well. But keep in mind this, we're using the proportional tail as the candidate method here. And for the struck out, same. So quite, the behaviors are quite similar, the characteristics, and everything on top of one another looks like this. So the blue ones are the world, the green ones are the limited, and the magenta ones are, well, it looks purple, but I set it to magenta, but the alpha is set to 0.6 so that they show. The magenta are the struck out ones. This is what it looks like. This is just a fun thing that I did. I don't think it's worth mentioning. Oh yeah, and these are this is one of the distributions, one of the sets of 3 distributions, namely the world group, limited group, and the struck out group. The age the distribution, sort of like a population pyramid, if you'd like. And then we can analyze the slopes. Yep, go down, go down. There we go. Aligning the slopes or groups. This is what it looks like. They all. I know this is hard to see. So let me just copy, paste it. Yeah, this is slightly better. So the green is the world. No, green is not the world. Blue is the world, green is limited, and magenta is, well, the struck out. This is from 0506_1, and you'll see that, well, at least the positive ratio is no longer 0. It was very close to 0, but now it's slightly less so. The one interesting thing is that the green line, which is for the limited entities, the positive slope ratio gets higher from time to time, or most of the time. But usually the struck out ones are, you know, they seem to be on a higher level. But if you think about it, they are struck out because they already had a somewhat of a, well, because they were going up in terms of some utility scores. Separately, we can have a look here. This is for the world, per learn rate in different colors, and this is the average of each color. This is still from 0506_1. This is for the limited entities. You'll see that it goes almost up to 1. And then this is the average per color or per learn rate for the struck out entities. This is what it looks like, and this is the average. One thing that I do speculate, or rather wonder if I'm right or wrong, is that, let me just zoom in just to try to verify if what I'm thinking is true. So that is definitely a point. I need something. That is definitely a point, and I am going to shit. That is definitely a point, and I am going to come. I'm so bad. Okay, let me try this again. Go to one of the points, and I want to draw a straight line for the limited all the way down to 0. Is this a straight line? Are these parallel? Yeah, it is parallel. So if I have a look here, oh, maybe I need another one. This is definitely okay, this one. This is definitely also where it started. Cool. So the positive slope ratio for the limited entities go up And when that happens, the positive slope ratio for the struck out entities go down. And I think that may be due to the fact that if we come back to the entity counts, if we go back, entity counts, when that happens, there are so few entities in the limited group, and there are, on the flip side, there are more and more entities on the struck out group. So if there used to be 3 entities, or if there used to be 10 entities out of 100 limited entities that had a positive slope, that had a overall positive slope, and then suddenly there are only, in the next run, or in the next iteration, in the next given conditions, different learn ratio and different candidate percentage, if there are fewer limited entities, but there are still about the same number of entities with a positive slope ratio. If there are a lot fewer entities in the limited group, but about the same number of entities that have a positive slope, then the positive slope ratio is going to be inflated, just like this. So this is where the inflation happens, and this is where the deflation happens, because now there are more, in this case, there are more struck out entities, and here there are a lot fewer limited entities. That's why the positive slope ratio just skyrockets for the limited and plummets for the struck out. And I believe the same can be seen here as well, or something very similar. If they go up, the positive slope ratio goes down. Yeah. Note that it says learn method here, and then because it's set to universal, then the different learn rate method is just stated as 0.0 or 0.1, just as simple learn rates. However, if any kind of a specific learn rate method is being applied, then it's going to have different names, such as here, proportional tail turn, like this. There are 6 of them, and when there are 6 of them, like this, they're not exactly in any kind of order. I mean, there is some kind of an order, but it's not like from 0, 1, 2, 3, 4, 5. So this is the world positive slope ratio for 2025-05-13, where the candidate method is proportional tail, and there are 11 universal learn rates. You see that the positive slope ratio starts going up, as you can see in the average per color, but it does hit some kind of a plateau there. For the limited entities, again, the positive slope ratio goes up, but because there are so few limited entities, it's very easy to inflate this ratio, but it still does hit a plateau. For the struck out entities, They go up, but they're nowhere near 0.5 or 50%. The positive slope ratio for the struck out entities, and these also do hit a plateau. So now that we have seen the plots that I'll be mostly covering in this part of the video blog, let's move on to the other notebooks after a quick sip of water. Okay, I'm back. So, as I quickly scrolled through, you might have seen the plots, but here I go anyway. So this notebook is 2025-05-13_1. This is where the candidate method is proportional head, meaning that if you have the world, seriously? If you have the world, the candidates will be chosen, like chosen, or the distribution, or the chances of being picked, maximum of not one, okay, one actually, but still it's proportional. Anyway, here all the way down to here. So the head entity is far more likely to be picked than the tail entity. Forget that. Tail entity. Before it was the other way around. The previous notebook, that was proportional tail. One. So just that's the difference here in this notebook. We go straight to entity counts, world. Again, similar pattern here. Higher learn impact, meaning fewer entities in the final world. For the limited entities, same thing. Fewer and fewer entities get limited out because they are being struck out first. And that is also shown here. And at the 0.3 mark, or 30%, learn rate of 30%, is where we actually start creating more entities, because more entities are being struck out than being limited. Here it was about even. Here now we're not. And total, yep, way above 20,000 and all the way to 47,000. Entity count ratio, about the same. Struck out to entity, well, struck out to world, about the same. Struck out to limited, about the same. And the lifespans we go on to, well, let's so this is still this is quite similar to this, except this bit, but overall we don't have any occasions where the average lifespan goes above 100 or even up to 250-ish. Everything is just here, all the way below 100. I don't know if that's a good thing or a bad thing, or if it's not a good thing or not a good thing or not a bad thing. I don't know. Limited average ages for the average lifespans for the limited entities. Again, same, but that's because I'm getting more and more struck out entities. Yep, and when we put them all together, this is what we get. This is proportional head, by the way, just as a reminder. Something I did for fun. And the slopes. Positive slope ratio is something that, again, we have seen. It goes up, spikes down, and for the struck out entities it's about the same. When they go up, the struck out entity, the positive slope ratio for the struck out entities just decreases and stays there for a bit until this point. Yep. And for the world, this is the positive slope ratios for the world per learn rate, and average per color or per learn rate. It increases and then it just hits a plateau and then just oscillates. For the limited, again hitting the very top, kind of, but because they're being inflated. Yep. That's wrong. I should have changed that. I hate it when this happens. I could have found this out earlier. Oh god, I feel so bad. How did I not see this? I'll come back to dealing with the slopes later. Ooh. So, skip the slopes. On to the next one. The next notebook is 2025-05-13_2, and we go straight to entity counts, world, entity counts, world. I really hope these aren't the same thing again. Not the same, thank God. Okay, same behavior there. More learn impact, meaning fewer entities in the final world. For the limited, again, white gaps because more entities are being struck out, and now we have more entities being created after the 0.3 mark. Learn rate of 0.3, more entities being created, and total, yep, count ratio, limited to world, okay, struck out to world, okay, and struck out to limited, yeah. And this is where the candidate method is exponential tail, meaning that the candidates for learning will be chosen while following a distribution like this. That's too generous. Something like this. This is tail, this is head. So the tail entity is far more likely to be chosen than the head entity. Oh, that thing about slopes is just really disturbing. I could have been more professional and spotted out that typo. Well, I guess I wasn't thorough enough. Yeah, and let's have a look at the lifespans. There we go. For the world, and compare this to the world lifespan. Limited average ages. Limited average ages. Yep. Struck out. And when we put them all together, this is what we get. It's well, interesting to see that they all kind of follow one another, except maybe here where the green ones, which are the limited entities, right? Yeah, the limited entities, the average ages for the limited entities get shadowed by the other two. That's something I did for fun again. Yeah. On to the next one. 2025-05-13 underscore 3 is where the what is it? 3 is where the candidate method is exponential head. So the candidates are chosen while following a distribution like this. Following a distribution like this. So the head entity is far more likely to be chosen than the tail entity. And this is the entity count. Same thing again. Limited entity. Struck out entity. Yeah, we see the same pattern at 0.3, and after that more entities being struck out and being well, created through procreation. And the maximum for the total entity count is 46,000. So that's about here or here. The ratio is still something that we have seen. Yep. And the lifespans, yeah. Lifespans, let's have a look at lifespans. Still, well, this one's kind of, well, unusual because it goes above 100, as opposed to when you compare this to these, where they don't really ever actually go over 100 in other cases. Yep, doesn't happen. But when we have exponential head here, it does twice, maybe also 3 times, thrice. Limited, does that mean we have lower numbers for the limited? Lifespans, limited. Not necessarily, no. It seems that having the candidate method set to exponential head, has increased the average lifespans for the limited entities. Let's see if that's the same for struck out entities as well. So it was at the maximum was what, 62, which I think is this one. No, the maximum is 70, which is this one. So it seems that favoring the top entities, favoring the top entities usually ends up increasing the lifespans of entities in all groups in the world, in limited and in struck out. Is that a good thing? I don't know. Everything on top of one another. There we go. On to the next one. This is the what is this? Oh yeah. So this is where the candidate method is normal distribution. It follows a normal distribution, meaning that the probability of being picked follows a distribution like this. So if you're in the middle, you're most likely to be picked. If you're at both ends, either at one of these both ends, you are, least likely to be picked as candidate method, as learn candidates. So there we go. Okay, same, and all together same. Yeah, 0.3. We have that. Okay, maximum being 47,000, so that's here probably. Entity counts ratio, same thing. No, not same, similar. You know what I mean. Okay. The texts are a bit smudged, but that's okay, because the maximum y value is at 206. The ratio is at 206. I think that's this one. And this is when the learn rate is at 0.7 and the candidate percentage is at 1.0, meaning 1%, meaning 100%. And that's because so many entities are being struck out, which means that a lot more entities would be being created through procreation. And lifespans, average ages for world. This is very different. This is normal, right? Normal distribution. Yeah. And we don't have any. Oh, we have this, which I think is quite unusual. When the learn rate is at 0.9, so 90%, and the candidate percentage is at 0.1, meaning 10%, we have the average lifespan for world entities at 99.89, so almost 100 generations. That's interesting. I don't know why that would happen. I don't know why it happens and then it just falters down. Yeah. Huh. We'll have to see. Yeah, on top of each other. Okay, that's fine. Did I get this? Well, yeah. Well, it's just that I got these wrong. Yeah, I just need to get these right. Yeah, I'll revisit these. So the next notebook is 0513_5. This is where the candidate method is at random or uniform, depending on what you would like to call it. And here are the entity counts. Similar behavior and characteristics. Yep. The count ratio. Very similar. Okay. Go to lifespans. World. We have one spike at where the average age for average lifespan for world entities is 106.86, and that is when the learn rate is at 20% and the candidate percentage is at 50%. And very similar here as well, but slightly lower. Yep, nothing unusual here. Okay, on to the next set of notebooks, and this is where it's 2025-0514, and from 0 to 5, so there are 6 notebooks, and this is where each notebook uses a different learn rate method. So the first one, this one, _0, uses the proportional tail for the learn rates. Well, actually, I did that wrong. Let me start over. It is almost the same. 2025-0514 uses 14 _0 to _5, so 6 notebooks, all cycle through the 6 learn rate methods. But the _0 means that it's going to be using the proportional tail candidate method. _1 means it's going to be using the proportional head. _2 means it's going to be using the exponential tail. _3 exponential head. _4 I think is going to be using the normal normal method, normal distribution. _5 is going to be using the random method. Yeah. For the normal and random, it just says tail here, but they're not. It doesn't mean anything. I just put them there for the sake of formatting. So the first one, 0514 _0. So both, in this case, are using proportional. Both the learn rate method and the candidate methods are proportional tail. Well, and then the learn rate method is going to change from is going to go from proportional proportional tail, and then proportional head, and then proportional whatever. Yeah, here, proportional tail, proportional head, xp tail, xp head, normal tail, random tail. It's the same order as this, but they're not in any kind of a numerical order. And just because proportional head is after proportional tail doesn't mean proportional tail is bigger than proportional head, or the other way around. So the entity counts. Okay, when we have a look at this, we can see. We'll try looking at this all together as many as possible at the same time. So we still see that a higher learn impact results in fewer entities in the final world, except maybe when using exponential tail for the learn rate. Or the exponential head. Yeah, I have a good explanation for that. So when you have the world, it doesn't look pretty. When you have the world, and when you have the learn rate following a certain distribution, or a certain shape of distribution, and when you use proportional head, proportional tail, or proportional head, the maximum learn rate is 1. So either the tail entity is going to have a very good learn rate, or the head entity is going to have a very good learn rate, and the minimum is almost 0 point something, or let's just say almost 0. And but the focus shouldn't be on either one of these two, head or tail. The focus we would have to be on the next ones, on the second entity, on the third entity from the top, or the second entity, or the third entity, or the fourth entity, from the bottom. So if the first entity, if the head entity has a learn rate of 1.0, the second entity is going to have something like something close to 1.0, but slightly less, so like 0.9 or something, let's just say. Yeah, let me just check. Where is it? Yeah. Sign rates proportional. Okay, I'm still checking. I haven't gone away anywhere. I just want to be sure about what I'm talking about. Where is it? I have so many notebooks. I don't even know what I should be referring to. I'm just so not organized. Learn rate, there we go. Alright, yeah, so I was right. So that's what happens. So for example, let's just suppose for making the explanation a bit easier, let's just suppose that it is proportional tail. Oh god, proportional tail. Proportional tail. Cool. Where this is 1 and this is 0. So that head entity is going to have a learn rate somewhere close to 0. And the tail entity is going to have a learn rate close to 1. And this is computed by, well, usually by dividing the rank dividing the rank by the number of entities in the world. So if there are 50 entities, the tail entity is going to get the number 50 here, and then we divide by the number of entities in the population. For the head entity, the rank is 1, not 0, but 1 in this case, and then we divide that by 50. You know, I could still divide 0 by 50 because that still works. But anyway, so this is 0.2, well, 0.02, sorry, and this is 100%, or let's just say 1.0. However, the second one from the bottom is going to be 49 over 50, which is 0.98. And the second one from the top is 2 divided by 50, which is 0.04. So a learn rate of 2% and learn rate of 4%, and then it goes on until learn rate of 100%. So when we have proportional tail and proportional head, regardless of what candidate method we use, the impact of learning is kept regardless of what, not regardless, but it is kept relatively well when we use exponential tail or exponential head, because things going from 0.0, 0.0, 0.2, and 0.2, 0. Let me just. I'm so bad at this. 0.0, 0.2, 0.2, 0.04, and all the way to 0.98, 96, 0.98, 1.0. This is all thrown out the window. It doesn't matter if this is reversed or not. It could be from 1.0, 0.98, and all the way down to 0.0. This is when this is when learn rate method is proportional head or proportional tail. This goes out the window when we use the exponential. When we use anything exponential for the learn rate method, because this is head, this is tail. Suppose it was exponential head, and then it goes like this, and then the maximum learn rate is 1, and then the minimum learn rate is somewhere here, which is 0. So for the head, it's going to be 1. And then next up, I'm going to be dividing by 1 divided by 3. and then it's for the third one it's 1 divided by 5, and then the 1, 2, 3, the fourth one is going to be 1 divided by 7, and this goes on and on and on. So if the rank is really low or towards the bottom, it's going to be 1 divided by 300, or actually 301, because everything has to be odd numbered. Every number has divided by odd numbers, because I usually increment everything by 2, and then it's going to be, after that it's going to be 1 divided by 303, 1 divided by 305, so this goes on. And when this happens, the overall impact of learning is greatly diminished, as opposed to when things used to be 1, 0.98, 0.96, 0.95, etc., all the way down to 0. So if you compare, the first ones are always going to have a learn rate of 100%. If it's tail, then the tail entity is going to have a learn rate of 100%. Same thing. But what matters is the next one. The next one is going to have a learn rate of 98%. Whereas when we use anything exponential, the next one is going to have a learn rate of 33%. And then down to 20%. Whereas the third one, in anything proportional, is going to have 96%. So a huge difference there. And that's why when we use the exponential head or exponential tail as learn rate methods, not many entities get struck out. The only entity, or the only entities across generations that are very likely to be struck out, are the head entities or the tail entities. That's why we never have the final world population below 1,000. And then we see the normal distribution, and then this is where we, things are as we expected. So back to the first one, proportional tail, and then proportional tail as well. See, everything is limited, and not much gets struck out. Yeah, for the same reason that I just talked about for the last 20 minutes. And everything on top of one another. Yep. There we go. And the ratios. Oh yeah. Okay, well, okay. Yep. Struck out entity count divided by limited entity count. Yeah, all the way down to 0. Okay. And we have a look at the lifespans. Wait, no, that's not what I wanted to do. The next notebook, same. I'm just checking if it's the same thing. Proportional head. What is this one? Limited. Oh yeah. Lifespan limited. No, it was entity counts. Entity counts limited. Very similar. Struck out. Quite similar as well. Everything together. Similar as well. Separate. Total. In total. Yep. I see. Exponential head. Same. Oh, see, there are still some things being limited. well, being struck out, I mean, but then again, the world, the population for the final world still doesn't change when we use exponential. Okay, normal distribution, candidacy is normal, follows in a normal distribution, still the same, okay, so very similar. Yep. Okay. Separate. Let's have a look at the total. Okay, total, there we go. Total here, total here, total here. Quite different. Let's just set everything here. I apologize for jumping from here to there and so, frantically, and I must have lost focus. So let me concentrate. Let me focus. So for the total entity counts, again, for the exponential family, we have about the minimum because we're not actually losing that many entities to the struck out entity group. Same across all candidate methods. Okay, what about this? Yeah, okay. So, moving on to lifespans. Plots. Lifespans, give me the plots. Lifespans. Lifespans. Am I at lifespans? Yep. Lifespans. Lifespans and lifespans. Cool. So the first one, where the candidate method is proportional tail, average lifespan for the world, for the entities in the world, looks like this. Proportional tail, candidate method, proportional head is like this. This is proportional tail, proportional head, candidate method exponential tail, right? Yeah. Exponential head, okay. Normal and random. Okay, let's have a look at limited. Proportional tail, proportional head, exponential tail, exponential head, normal, random. Not that different. Quite similar, I must say. Yep. Okay. For this is limited, struck out. Okay. Proportional tail, proportional head, exponential tail, exponential head, normal, and random. Okay. And everything together. Ah, well, normal tail. Normal. Seems to have the learn rate method. Normal seems to kind of guarantee entities in the world the longest lifespan, average lifespan. That's interesting. Normal tail. I don't know why. And as a reminder, when there was no learning and no shuffling, the average lifespan for entities in the world was 27.139. For the limited entities, it was 39.5. For struck out, it was 7.3. And after shuffling, it was for the world it was 39. For limited, it was 36, and for struck out, it was 6.3. Well, at least now they're all above 30-ish, I guess. Let's see if they're all kind of above 40. Yeah, they are. They are kind of. Except these ones. So this is exponential tail. Okay. That's good. And for the very first, and for the candidate ranges, if we go have a look at this one, yeah, they're all kind of, no, they're not. So that's odd. Okay. So that's about it for this part, and that was 90 minutes. Holy. And in the next part of this session, I'll revisit the slopes part when I fix the typos, my mistakes, and rerun all the notebooks. And then after I have had a look at those across all 13 notebooks, then I can have a look at the distributions, the entity distributions of the final world, and then the average summed utility plots for the world, not for individual entities, but for the world. So basically I'm looking at the same things, but I found out that looking at the entity distribution of the final world state and then having a look at the world summed utility plots is better, because it gives me a more robust grasp of understanding of the issue, of the state that the world is in after 500 generations, or after the iteration has been completed. So thanks for watching. See you next time. See you in a bit. Bye.